Deep circuit pin-to-pin capacitance. We have a circuit with 16 pin contacts. Our task is to calculate mutual capacitance between any two pins. Probably the most prominent is the capacitance between two pins placed close to each other. So I am going to calculate mutual capacitance between pins number 1 and number 2. Relative dielectric permittivity of the plastic is 3. To calculate capacitance, I should simulate electrostatic problem. I will assign positive and negative potentials to the pins. QuickField would calculate electric field distribution and the stored energy. And the capacitance is then double energy divided by the potential difference squared. So let's start QuickField now. Here I create new problem. Socket. Next. Problem type is electrostatics. Model class is three-dimensional import and length units are millimeters. Finish. On the left you can see the problem tree and on the right you can see the geometry model editor window. As I specified the model class to be three-dimensional import, the only option here is to import the geometry model. So I click Import Step. Step file is used by the majority of the CAD system to interchange three-dimensional geometric models. So this is the model to import. Open. The model was imported. Now here, to distinguish one geometric object from another, I should assign labels. To assign a label to the object, I should select it. So I click it and the face is selected. To select the body, I should click the selected face again. Now the body is selected. This is the dielectric. You see the label appeared in the tree, and if I double click this label, I can provide physical properties. For this dielectric, the relative electric permittivity is 3. OK. Now let's hide the dielectric block so I can see better what we have inside. All pins are made of the same conducting material, so I can assign same label to all pins. Right click and drag to select them all. Now for the bodies I type in the label conductors. In fact, there is no electric field inside conductors, so I will not specify any electric permittivity value here. You see the label icon has the question mark. This means no field will be calculated in the objects with this label. It is true that in the conductors there is no electric field, but you should specify electric potential on the conductor faces. So let's again select, and this time I will assign label to the faces. This is pin number 1. Select another pin. This is pin number 2. And same way for all other pins. Now I have finished labeling faces of the pins. If you click any label, you can see the corresponding object. Now let's provide physical properties. As I said, I would like to calculate the capacitance between two pins. So for two pins I should specify positive and negative electric potential. These could be any two pins. I would like to calculate the capacitance between pin number 1 and the pin number 2. So for these two pins I provide electric potential. Pin number 1 will have electric potential plus 0.5 volts. Pin number 2 will have electric potential minus 0.5 volts. What about other pins with question mark? These pins are not connected to the source, so for the faces of the pins I specify floating conductor, equal voltage. And the same for all other pins which are not energized. Okay, I have finished with all pins labels. Now let's unhide all objects and check the model. In our model we have the dielectric medium, we have conductors, and for the conductors faces we have specified electric potentials. For the pin 1 we have specified positive potential, for the pin 2 we have specified negative potential. All other pins are marked as floating conductor. Our model is almost complete. We have only one missing block, the air. Electric field distributed not only in the plastic case, but in the air surrounding the socket. So let's add the air in our model. Background region enabled, yes. Now you see the air body is added to the model, and we should assign label and physical properties to this body. First click to select the face, second click to select the body located behind this face. This would be the air. And for the air I specify electric permittivity of 1. Before we start the analysis we should build the finite element mesh in the geometry model. It could be done in 3 stages. First you build the finite element mesh for edges. Then you build the finite element mesh for faces. I must admit I do not like the mesh quality here. You see, we have built the automatic mesh, and in automatic mesh QuickField chooses the mesh element size depending on the geometric object dimensions. Small object, small element size. Large object, large element size. And the element size affects the result's accuracy. So I better select everything and switch the spacing to manual. Spacing for the deep socket is quite good enough, so I leave it as it is, but for the air block I will set the spacing to be smaller than this. Air block dimensions are about 10 by 30 millimeters, so I will set the spacing to be 2 millimeters. Now that seems better. Let's again build the mesh on faces and build the mesh in volumes. The mesh is ready. You can see how many nodes of mesh we have in the geometry model. About 270,000 elements. Now let's save all simulation files and run the solving process. The problem has been solved and we can take a look at the results now. Here you can see the electric potential distribution over the air block's faces. Again, we can hide some bodies to take a look at the field distribution inside. Hide. You see, indeed we have 2 pins with positive and negative potentials assigned, and the potential difference is 1 volt. Now let's calculate the electric field energy. I will unhide all, select everything, and use the integral tool. And here you can see the stored electric energy. Now if I take double value of this energy and divide them by the potential difference squared, which is 1, I will get the capacitance between two adjacent pins. Hiding blocks is not the only option to look at the field distribution inside. For example, I would like to use the electric field stress distribution in the air. So I will switch the presentation type to the strength and use the cut by plane. You can change the plane orientation and you can adjust the plane position. To get a better picture, you can switch on the two-dimensional section window. And here again you can adjust the field picture. You can switch to the electric field strength, switch off the isoline plot. You can take the field value at any point. Or you can use the contour tool to get the field distribution along the line. The values used to build this plot you can see in the table. If you search for the deep circuit capacitance, you will find the example page at our website, and here you can read about problem setup, browse for the solution section, take a look at the resulting picture and download the simulation files. Simulation files may be viewed using any QuickField edition, including free QuickField Student Edition.